7.3 notes, multivariate linear systems and row operations.
Multipass. Have you ever seen the fifth?
The sixth sense. You have 5 senses.
Dang it. Never mind.
Okay, let's just go with the notes.
Let's do.
We're going to solve systems with more than 2 variables.
The fifth element.
And, no, I haven't. Okay. And we're going to do that a few different ways. We're going to start off here with elimination. So this problem,
brush off your algebra skills.
Yeah, this problem here, 6x minus 5y minus z equals -2. And then we continue on. When we eliminate, that's where we're trying to add 2 equations together so that a variable goes away.
Right. We're going to eliminate a variable.
Right.
Yes.
And with 3 by 3 kind of situations like this, typically it doesn't matter which variable we eliminate first, but in this case, it actually will be helpful if we look at this middle equation. It's missing a y.
Hey, so let's try and dump the y's.
Right, and in fact, if you look, the y's, all you have to do is add these 2 equations together, and you'll eliminate the y's.
Looky there.
So let me set this up. I'm going to take the first equation and the third equation. And these can get kind of long, just a spoiler alert.
You'll need some paper. It's quite possible you'll need some paper.
Okay, so we're adding these together. It gets rid of our y's. 10x plus z equals 14. Okay, now normally we would have to do that again now and eliminate y again, but this other equation already has y eliminated for us.
So we can just dive right on in.
Right, write it underneath. And, whoa, this even has it set up.
Hey, man, what a great question to start with.
So these 2 add together and get rid of our z's, so that's 7x equals 14.
Oh, look at that, and it comes out nice.
So x equals 2. Now, you take that and you plug it back in someplace where you have 2 variables. So we have 2 variables right here and right here. So either of those equations would work. It doesn't matter which one you pick.
You're basically working back up from where you were. So we worked all the way down and eliminate all the variables until we just have 1. Now we're going to go back up, because if we try and substitute the 2 into one of the problems,
like the first
or third one, we still have 2 variables left to deal with.
Yeah. So here I am solving for z once I plugged in x. So z equals -6, and now I have x and z, so now I go back to one of these original equations. Back up one more. So it doesn't matter again, so I'll pick the first one, 6 times x, which is 2, minus 5y, minus z, which is -6, equals -2. So that's 12, which will write down 12 minus 5. -6 is really a +6. So that's 18, adding like terms. Subtract 18. -5y equals -20. Divide by -5.
And you get
y equals 4. And the way you typically will want to write this is as a 3-dimensional point. That's what this is talking about here. 2, 4, -6, which is x, y, z. So just like a point x, y.
X, Y, Z.
We can have a 3-dimensional point. That's what this kind of problem could be representing, as a 3-dimensional problem.
Right.
And that would be 3 lines where this is the point where those 3 lines intersect.
Right, right. Same rules apply here too. If you get like some wacky thing like 0 equals 4 or
0 equals 0.
Or 0 equals 0.
You have a special case.
You have a special case, and those are both okay to get.
Yeah. All right, let's try another one. This is one where we have 3 variables and 3 equations. This is a y down here and kind of got cut off, at least on mine. Maybe it didn't on yours. But the idea here, and this is the tricky part, is starting this off. The idea is we want to pick either x, y, or z to eliminate. And it doesn't matter which one you pick. In this particular case, it's about as easy to pick any of these, really. Like, it really doesn't matter which one you pick. You can do any of the letters easily. So I am looking at the first 2 equations, and I say, well, I can really easily eliminate the x's. And so I would want to multiply one of my equations by a -1 to make that happen. So I have the first equation is x plus y plus 2z equals 11, and now I'm going to multiply by a -1 on the second equation. And I'm going to add through to eliminate. So the x go away, and actually this is nice, the y's go away as well. And that might freak you out at first, but that actually makes things simpler for us. Negative z equals negative 3, which means z equals positive 3. Now, that worked out really nicely. Now we already have what z equals, but we don't have any place where we have an equation with just two variables to plug that into. So even though it was nice that that happened, we still are going to have to come back over here and eliminate again. Typically, in a problem like this, we would want to eliminate the x's again. We don't have to here. We could eliminate the y's, but let's go ahead and eliminate the x's again. So I can actually do the last equation, x plus 2y minus z equals 5, with, again, negative 1 times the middle equation. So negative x minus y minus 3z equals negative 14. And now add the equations together and let's eliminate. So that gives us y minus 4z equals negative 9. Now typically we would have on our first one gotten like y minus z equals negative 3. On the second one we have y and z. So typically what you would have to do in that situation is put those together and eliminate again. But that didn't happen. We just have z equals 3. So we're going to plug that in to this equation that we just got. So y minus 4 times 3 equals negative 9. So y minus 12 equals negative 9 plus 12 on each side. And you get y equals 3. Now take it all the way back to the beginning. And I'll just use the first one. It looks easy enough. X plus y, which is 3, plus 2 times z, which is also 3, equals 11. 3 plus 6 is 9. Subtract 9. X equals 2. So our point here, x, y, z, is 2, 3, 3. Now just like with two variable equations, we can take that and we can plug it back in. If we got a number and we were feeling unsure if that was the right answer, you could plug it into any of the three equations or all of the three equations up here and check to see if what you get works out, if it's really a solution or not. Okay, so we talked in example 1 and example 2 about solving a system of equations with elimination where we've got 3 variables, and we could do that same thing if we had 4 variables or 5 variables. But the more variables you get, the harder it is to keep track of things, because like if you have 4 variables, you have to eliminate a variable. Well, then you have 3 variables. So then you got to eliminate another variable, and then another. So there's another way of doing, once you get up to 3 variables here, another way of doing things you use matrices for. It's okay. You use matrices for. So just to get us started on the idea behind matrices, we're going to rewrite this system as an augmented matrix and as a coefficient matrix, just to see what that looks like. That's our first step in heading towards using matrices.
And this is actually really cool, using these matrices, how it all sorts itself out.
Yeah.
I think.
So with an augmented matrix, you want to tell them?
Yeah, what you're going to do with an augmented matrix is you're basically going to fill the matrix in with the numbers that are in front of the variables.
Right, so we have like an x column, so that's 1, 1, and 1, because that's the coefficients.
That's what they are.
Yeah, and then you've got a y column, 1, 1, 2.
Yep.
And then a z column.
2, 3, negative 1. Now keep track of those negative signs, because that's where you'll get important. A whoops.
And then a lot of times you'll see a line here. That line goes where the equal sign in our equation is. And then the next column is the right-hand side of our equation. So here I'm abbreviating right-hand side RHS. So
11, 14, 5. Now, every now and then you'll see some different notation where Mrs. Stevenson's put that line. Sometimes it's like a couple of dots. Sometimes it's different things. But that always means equal sign here.
Right. It just helps you distinguish where the equal sign would be if you were rewriting it back this way. That's the augmented matrix, and it's augmented because it's got this extra thing out here. A coefficient matrix just has the coefficients. So it would just be the first part of this. So 1, 1, 1, 1, 1, 2, 2, 3, -1. Where we've just taken the x's, the y's, and the z's out, we leave off the right-hand side.
Do we put in the right-hand side anywhere?
Not for a coefficient matrix.
Do we put in a variable matrix, like x, y, z?
We'll do that later.
Okay.
Yeah.
Good talk. Row echelon form of a matrix. This is tough stuff potentially.
Yeah. So we basically, when we're dealing with matrices, we can use them to solve systems of equations.
Right.
And the more variables you have, the easier it is to do it this way versus
Right.
elimination or substitution.
You got x and y only. Elimination, substitution's not too bad.
That's the way to go.
You get x, y, z or w, x, y, z, and it gets very challenging.
Right. And so there's this row echelon form is just where you have in your diagonal ones, and underneath your diagonal you have zeros.
Right.
And so as long as that is the case, that each row, the first non-zero number is a 1.
Right.
And then everything underneath that in the column has to be 0.
Right.
Now, there's also a thing called reduced row echelon form, which is this right here, which takes it a step farther.
Which is even more work.
Right. Not as much as you might think, though.
Not as much, but
that also puts zeros up here. And what happens is, if you think about changing this to a system of equations, this is saying x equals 2, y equals 3, z equals -7. So if we get to reduced row echelon form, we have
game
the
on.
answer.
Yeah, we got the answer.
With regular row echelon form, you still have to do a little work, because this is saying z equals -2.
Now we work back up.
Right, because this is y plus 4z equals 5. So you plug in and then plug in again.
Right.
Now, if we put a system of equations into an augmented matrix, these right here are the things we're allowed to do, the row operations.
This is
what we call them.
basically your algebra. It's basically your algebra rules, but they apply to the matrices.
Right. So
Okay.
we are allowed to interchange any two rows. So if like row 1 and row 2, if you'd rather they be the other way around, you
Not a
can
problem.
do
Yeah, totally legal.
that. Number 2, you can multiply all elements of a row by a non-zero real number.
You can't use 0 because 0 times anything is
Zero,
Zero,
and that's not helpful.
Yeah, it doesn't
to make
do
a whole
anything.
row 0. And then the third step is you can add a multiple of one row to any other row, and that's where it gets a little tricky sometimes.
Right. But that's exactly how elimination works. If you think about it, you're adding a multiple of another row to some other row.
Right.
So
now this can potentially take up some room, so you want to write small. I don't remember how much room we gave you guys on this. We just start off by writing this as an augmented matrix.
So step 1, don't mess up step 1.
Right. If you and actually, whenever you're like, I got stuck and don't know where to go, the first thing you should do is make sure you wrote it down right.
Right.
Otherwise, you're going to be hunting for
And
a
if you don't get the
mistake.
correct answer when you do this at the end, oftentimes it's almost easier to just start over than to go through and find the mistakes. Not every time, but a lot of the time. So just be prepared to do some erasing.
Right. Now, first off, like, pay attention as we go through this. This is the legit easiest way to look at this, and I have done this so many times that, like, I'm an expert at this.
And I don't doubt that.
Like, because I've taken classes where, like, you do this stuff all the time.
Yeah.
So,
I've seen what you do, and she is not lying.
So trust me, if I tell you you can or can't do something, like, I know what I'm talking about.
On a matrix, for sure.
So the first thing I see here, because we're trying to get row echelon, so we're trying to get
top
this,
one. Right.
but probably different numbers up here.
Right, different numbers.
We start here and work our way down.
That's a brilliant plan.
So we want to get this 1, and if you look, since we're allowed to switch rows around, we might as well switch the first
Might as
two
well.
rows.
Look, it's already a 1, so let's just go ahead and do that.
You typically, when you do this, you note what you're doing,
so
out
that
to the
we
side.
know what you're doing.
And so this is the notation for switch row 1 and row 2, which hopefully that notation makes some sense. So this will be 1, 2, -3, 12.
And all we're doing is we're following step 1 under elementary row operations on the matrix. We're following step 1 in that bottom green box.
Right. So row 3 didn't have anything.
No, nothing
changed.
happened, so it stays the same.
All right. Now, to get we got a 1. Now we're trying to get the zeros underneath. And what you want to do is you want to use row 1, because it's got a 1.
Right.
To get those zeros, because what could we add to 3 to get it to be a 0.
A -3.
Right, so what we're going to do is -3 times row 1, and we're going to add it to row 2. And the way this notation works is that only the second row is changed by this.
Okay.
Start off with, we're going to do -3 times the first row, add it to the second row.
Right.
So the only row that's going to actually change is row 2. So you can go ahead and write what row 1 is.
And you can go ahead and write what row 3 is, because we're not messing with that guy either.
Right. All we're changing is row 2. So what we want to do is think about, if I multiplied each of these elements in row 1 by -3, what would I get? So I'd get
-3, -6, 9, and -36. Don't forget those guys on the other side of the augmented matrix. You'll forget about them, and that's one of the easiest mistakes to make.
Right.
So
now we're going to add these to row 2. So -3 plus 3 is 0.
Yes.
-6 plus 7 is 1.
Right.
9 plus -11 is -2.
Right.
-36 plus 44 is 8.
Excellent.
Okay, now we've got that 0. Now we want to get the 0 underneath it. And these two steps you could combine if you wanted to. I'm just doing it separately because, you know, we're walking through this.
Right.
So let me come down here. If we want this 4 to be a 0, now we're going to times by -4 times row 1.
So
and for this
-4 row 1.
This first column that we're getting,
row 3.
We're just going to keep using row 1 to do our work.
And this time row 2 doesn't change because we're not messing with it. So we can actually copy down row 1 and row 2.
So let's see. We're multiplying, and this will be -4,
-8, +12, -48.
And then adding it to row 3. So
Right.
that's 0.
Right.
-8 plus 9 is 1.
Right.
12 plus -13 is -1.
Yes.
-48 plus 53 is 5.
Right.
Okay, so we're done with the first column. Now everything we do from here on out is structured so that we don't mess up the first column.
That's right. First column's he's finite.
Yeah. So the next goal is to get the 1 in the middle.
Yes.
And this is for regular or reduced row echelon form. We need to get the 1 first. And actually, we already have it.
Yeah. So we don't have to do anything.
So we're going to go and get the 0 at the bottom. So to get that 0 down here,
you just subtract. All
we
we have
would
to do is subtract.
R2 and R3. So we're changing R3. So we're actually doing -1 row 2 plus row 3. Okay, and it matters that we think about it that way because you are liable to mess up if you don't.
Yeah, that's correct.
We're changing row 3, so we times this row by a negative so that we can add.
So row 1 stays the same. Row 2 stays the same. So the only row that's actually going to change with this one is the 3rd row. So you can go ahead and fill in the first 2 guys.
Okay, and now
and we should keep a 0 there, by the way.
Right, this will be 0, this would be -1, that would be 2 and -8.
Yep.
And add them to the bottom.
So
0, 0,
right,
1,
right,
-3.
There you go.
And so then our last step normally for row echelon form would be to get this 1, but it's already there.
But we already have it.
So we rewrite this as a system.
And once you rewrite it as a system, it'll be a lot easier, I think, to see what you need to do.
It's a much easier system to solve than what we started with.
It's totally easy because now we know what one of the variables is, and so now how we worked down through all these steps, now we work back up through all these steps. We know what z is to start, so we go to the next place where we can plug that -3 in for z and only have one variable left.
So I'm just doing normal solving stuff here. Z, y, now I plug it into the first one and get x, so x plus 2 times 2 minus 3 times -3 equals
12.
And that's x equals 4 plus 9.
Right.
Which is, I didn't
x
mean
plus.
equals. X plus
4.
4 plus 9 is 13.
X plus 13 equals 12.
So x equals -1.
So our solution then is where
-1,
all of these things
2.
go together at a specific point. X, Y, Z. Alphabetical order.
Got it.
All right.
This one is a similar kind of problem, but this time it says to find the reduced row echelon form.
Yes, so that means that we're going the whole way?
The whole way. So
Whoa.
1's in the diagonal, 0's up above and below. And it's not that much more work than it is to find row echelon
You would think,
form.
but it actually is, once you get your row echelon form, the reduction part actually, it really isn't that bad because you've done most of the work.
Right. And so what you want to do, kind of like what we did last time, you want to start off by getting a 1 in the first column, 0's below, the 1 in the second column, and then the 0 up above and below.
Right.
And you always want to start off getting the 1 in a column because you're going to use that to get the zeros.
Right.
So let's start off and write this as our augmented matrix.
And make sure, again, as with the previous problem, if you run into errors when you're doing this, double check to make sure that you wrote the augmented matrix down correctly. It's almost impossible to go through all of your work and find that single mistake.
It can be really difficult without comparing it to somebody else's work that has already done it correctly. So we already have a 1 in the top left. That's great. So we're going to do row operations to get zeros below that 1. And so anytime you want a 0, I can't stress this enough, you use the row that already has a 1.
Right.
You multiply by negative of whatever you need. So here's a 3. So
negative 3.
Yeah.
Negative 3.
Negative 3, row 1 plus row 2. Okay, now, and we're only changing row 2, remember. We're going to use row 1, okay, but we're not going to change it. All right.
And we're not changing the last row. That's why Mrs. Stevenson is writing it down.
So we're going to do negative 3 times 1 plus 3. That gives us 0.
Yes.
Negative 3 times 2.
Negative 6.
Plus 7.
Negative 1.
Negative 6 plus 7 is 1.
That's why it says 1.
Okay. Negative 3 times negative 1 is positive 3 plus a negative 3.
0. I knew that one.
Okay. Negative 3 times 3 is negative 9 plus 12.
3.
Okay. Now, it really, like, this 0 is here, and that could work out really nicely for us, but it may not. Like,
it might not.
So don't look too far ahead and be like, oh, there's a 1 here.
Hey, yes, I got a 0. Woo.
Yeah. It really just, you have to go in order, and you can potentially mess up something that looks like it's going to be good.
This is not a Rubik's Cube.
So,
follow the pattern the whole way.
Isn't that like a Rubik's Cube?
Yeah, but on a Rubik's Cube, you're going to like, oh, I got that one red deal over here, and you try and get to it. Yeah, you don't want to mess it up.
So now I want to get rid of this 2. So this is negative 2 times row 1 plus row 3.
And so rows 1 and 2 don't change. You know what? I think if you just tap part of the screen cap, it goes away. Maybe there it goes. Okay.
What am I doing? Oh, this is going to stay the same.
0, 1, 0, 3.
So we're going to do 2 times negative 2 times 1 is negative 2, plus 2 is 0. Negative 2 times 2 is negative 4, plus negative 4 is negative 8.
Yes.
Negative 2
almost
times
said
negative
0
2 is 2, plus 3 is 5. Negative 2 times 3 is negative 6. Negative 6 minus 5 is negative 11. Okay. So it does look like this 1 is set there, like that
Leave
worked
the
out
one there.
really
Yeah,
nice.
it's going to work out great. But
And
we don't know that until we get to this point.
Right. Now that we're done with the first column, now we can move on and say I've got the 1 there. So now we want to get a 0 here where this 2 is and a 0 where the negative 8 is. It doesn't matter which one we do first. In fact, we could do it both at the same time.
Oh, I don't know about that. That sounds crazy.
What you would do is you'd say, well, for the first row, we need negative 2 times row 2 plus row 3. Okay? And then for the bottom row, we need to times by 8. So 8 times row 2. Did I say? I meant row 1 there.
Yeah, row 1. I was watching but not correcting, and I'm sorry about that. That's row 1.
Because this one's
row
row
3 is on the bottom, yeah.
Okay, so that should make sense. We need a negative 2 to cancel out on row 1. We need an 8 to cancel out on row 3. So we're going to do those one at a time. We're just only going to rewrite the matrix once.
So the middle row doesn't change at all. So you just slap it in there.
Okay, and so here we want to do negative 2 times row 2. So 0 plus 1 is still 1. which is good. That's what we want. Okay, -2 times 1 is -2, plus 2 is 0. -2 times 0 is 0, plus a -1.
-1. God, man, I got these.
And then -2 times 3 is -6, plus 3.
-3. Man, I'm on it. I'm so on it, K-Steve 320.
Right. So now let's do 8 times row 2 and add it to row 3.
Okay.
So 8 times 0 is 0, plus 0 is 0.
That's all zeros.
8 times 1 is 8, plus -8 is 0.
Right.
8 times 0
That's
plus
0.
5.
That's 5. 0 plus 5 is 5.
Right.
If I have 0 and add 5, I've got 5.
You're right. 8 times 3 is 24, minus 11.
13.
13.
Well, how do I get that 0 up there where the -1 is? I don't understand.
Okay, well, first, we're done with the second column. And so right now, we need to sit here and get the 1 first.
We're going to get the 1 first, so we have to divide by 5.
Right. See, and that's the way you get ones. Unless you can switch rows to get ones, which at this late in the game, switching rows is not going to happen. So anytime that happens that you need a 1, you multiply
by the reciprocal.
So we want to multiply this by 1/5. And to do that, we have to multiply that whole row.
Yeah, and don't forget here, again, common mistake number 1 is to forget that 13. You don't want to do that in this case.
No, you don't. That'd be terrible.
It'd be horrible. It'd be like cats and dogs living together.
Yeah. So, only row 3 changes here. And when we do 1/5 times 13, that's 13/5. I assigned Mr. Hazelwood the task of plugging this in to make sure we did it right. Because I don't know if that fraction, it's kind of a warning sign to me personally, but we're going to check and see. If that is right, then now our last step, because we've got a 0 here already, we just need to finish off and get a 0 up in this top right corner. And so to do that, we just need to add row 3 and row 1. And we're trying to replace row 1, so that's what goes second. But we don't need to multiply it by anything. So 0 plus 1 is 1. 0 plus 0 is 0. 1 plus -1 is 0. 13/5 plus a -3.
We're in there.
Gives us does it give us -2/5 if we do?
It had better.
Yeah, because
everything else is correct.
-3 would be -15 over 5. So yeah, that gives us -2/5. And then 0, 1, 0, 3, and then 0, 0, 1, 13 over 5. So the beauty of this, even though it was a little more work, is now we know the answer.
We know the answer without having to do anything else. And you know what? You have to do this work. We did this work anyway on the other problem. We just had the variables in there. So, but in this case, we worked it out inside the matrix.
And if you're not comfortable skipping or like doing the 2 steps at once like I did, that's fine. If you are comfortable doing that, then it really is like there's almost not any more space taken up on your page.
Right, there you go.
So that is reduced row echelon form. Example 5.5. We can split a system of equations into 3 matrices where we have the coefficients times the variables equals the right-hand side.
So this is like the augmented matrix idea where you take the different pieces
and you split them up. But you're splitting them up differently. And the idea here is if you put this into your calculator and you put this particular matrix in as A. Okay. And then we think of our variables, let's think of them as just X, right?
Okay,
they're variables.
sounds good. All right.
And then if we put in this matrix that's the right-hand side, if we put that in as B,
right,
how would we solve an equation like this?
You divide both sides by A.
But we can't divide matrices. Okay,
I have an idea. You multiply by the inverse.
That's correct. To move this A so that we'll have it solved for X, we multiply by the inverse of A. And this is actually something you can do in your calculator, like,
we'll have a video on it. We'll do a video on it.
We'll do a video on it, and like you're going to plug these into your 2 different matrices options, and then you literally type in matrix B times matrix A, and then do the inverse one button. Right. And then.
So I'm doing that right now?
Yeah, let's do that.
So Mrs. Stevenson told me to do this ahead of time, yet here I am, chatting it up with you guys. So get rid of that scalar.
Yeah. So 1, 1, 2. You know, I'm an 84 fan as far as the calculator goes, in general. But I would much rather do matrices on an Inspire. They are so easy.
And this is 3 by 1?
Yeah, 3 by 1. No pressure. And then
inverse.
I know on the 84s, I think that multiplication sign between them is pretty important.
Oh, you know what? I'll go ahead and add that on the Inspire too, just in case, because sometimes he wants it in there.
Yeah.
So.
And then you just put a -1x.
Whoa.
Do you have to do it the other way? Does it have to be A inverse B?
Maybe it's got to be A inverse B. So.
Oh, yeah, that makes sense actually. So everything we said is still true, but the A inverse has to come first. We're gonna multiply both sides by A inverse, and that's gonna get rid of this A, but A inverse is gonna have to come first in the calculator because this is a 3 by 3.
Order is important
3
here.
by 1.
Yeah, so we needed to follow our own rules we gave you for multiplying matrices, and we did not do that. And when you're done,
what your answer is X, which was a matrix with X, Y, and Z, and it equals
2, 3, 3.
Now, in 7.2, there were these nice couple problems where you just literally had to match up the elements and tell them what those letters were. Well, that's what's happening here. X equals 2 because they're both in the first spot. Y equals 3. Z equals 3, right?
Yeah.
So 2, 3, 3.
That's your solution. And chitty chitty bang bang. See you later.